Well, I want to bring an example showing that how to get the matrices representing for linear transformation as well as the change basis. Okay, now here we have R3. R3 is a vector space in which that all the vectors are three-dimensional, and R2 is a vector space, well, which consists of all the two-dimensional vectors. Then we have a linear transformation. Linear transformation, it is actually calculation of the mapping from one vector space to the other, like a real valued function that we correspond in the one set of real numbers onto the other. So the linear algebra is we play a game with the vectors instead of real numbers. Now we have a particular transformation. This is a R3 vector. This is R2 vector, and this is the mapping. This is linear transformation. From ABC becomes A plus B and a minus C. This is just specific linear transformation, right? Like functions, you have so many functions. You have so many linear transformations. Now, in this R3, the R3 that all vectors are three-dimensional, and we can have a basis. Well, what's the basis? Basis is a set of vectors which is linearly independent, and they generated the whole space, which means that, for example, B1 is a set of these vectors. These three vectors are linearly independent, which means that these three vectors are not coplanar. It's not on the same plane. None of them can be expressed as a linear combination of the other two. So that means linear independent. And these three vectors generate the whole space, which means that any vector in that vector space can be obtained by linear combination of these three vectors. Of course, you can have an infinite many bases. For example, the B2 is another basis because these three vectors are linearly independent and they generate the whole space of R3. Okay, of course you have infinite many bases. I just pick up two, all right? Two. And same thing as for R2. For R2, I pick up two bases, B3 and B4. B3, this is one basis for R2 because these two vectors generate the whole space of R2, and so is B4. And also that we have a standard basis. BS3 is a standard basis for R3 space, which means this is a standard 1001, and the BS2 is a standard basis for R2. Okay, that's the general picture for the general picture for this linear transformation and the structure. Now we have a matrices. Matrix A representing the linear transformation from basis of B1 to basis B3, and B is a matrix representing the linear transformation from BS3 to BS2. And C is a linear transformation, is a matrix representing linear transformation from B2 to B4. And D is a matrix representing the change of base 2 to base 1. And the D inverse is a matrix change of bases B1 to B2. And E is a change of basis, is a matrix change of basis from B3 to B4, and E inverse is a matrix change of basis from B4 to B3. And F is a matrix change of basis from B1 to standard basis, and F inverse is vice versa. And G is a matrix change of basis from B3 to standard basis, and G inverse is a change of the basis from standard basis to B3. Okay, this is a general picture, and now we just want to find these matrices. We want, well, technically speaking, how do you find these matrices? Okay, let me do one by one. First is A. Let's find A, okay? What's A? A is a matrix representing a linear transformation from B1 to B3. That is another way of writing it. Transformation from B1 to B3. Now, how to get it? Now, you write first to get linear transformation for B1. So what's the B1? B1 is this. This is B1. This is linear transformation. According to the definition of the transformation, this vector has to become A plus B. 1 plus 0 is 1, and the negative C, negative 1 is negative 1. And this vector, according to the transformation, is 1 plus 1 is 2. Okay? And negative 0 is 0. And this vector in the basis is 2 plus 2 is 4. Negative 3 is positive 3. So this is a matrix representing the linear transformation for a vector in basis 1. Now then, because the A is a linear transformation from B1 to B3, so we have to change this matrix operator into a matrix operator, change B1 after transformation into B3. So this is the way. You have augmented matrix. This side is the transformation for B1. This side is B3. B3 is the basis for the R2. 1 1 1 1 0 1 1 1 0. And then you perform row operations until you get the row reduce the row echelon form. This side is identity. Then this is my matrix A. So this is the matrix A, which is the linear transformation from B1 to B3. So A is a matrix which represents the linear transformation from B1 to B3. And now calculate B. Now B is what? B is a linear transformation from BS3 to BS2. Okay, this is another way of writing it. First, writing the linear transformation for BS3. BS3 is this. Transformation is this. So according to the transformation, the first vector is 1 plus 0 is 1. This negative 0 is 0. And the 0 plus 1 is 1. Negative 0 is 0. 0 plus 0 is 0. Negative 1 is negative 1 here. So this is a matrix transform for BS3, the basis of R3. Then we have to, because B has to change to base BS2. BS2 is this, right? Standard basis. So we write BS2 here, write this transformation matrix there, perform row operations. You don't have to perform row operations because this has been already in the row reduced the echelon form. So this is my B. This is my B. B is a matrix operation from BS3 to BS2. Now then for C, just same thing repeat again. C is representing linear transformation. C is a matrix for linear transformation from B2 to B4. From B to B4, another way of writing it. And B2 is this. B2 is this, right? This is B2. This is transformation. According to the definition of transformation, so 3 plus 1 is 4. Negative 1 is negative 1 here, right? Second element, second vector, 0 plus 0 is 0. Negative 1 is negative 1. And negative 1 plus 2 is 1. Negative 0 is 0. So this is a matrix for transformation for basis 2. But it's not enough because we have to transform into basis 4. So you write basis 4 here. This is basis 4, right? This is basis 4. So basis 4, 2, 1, 1, 0, 1. And this is the matrix, we just get it here. Then perform row operations until you get row echelon form here, reduced. And this is my C. C is this. So this is a matrix representing this is a matrix operation from B2 to B4. Okay. Now let's find a D. Find a D, okay? D, what's a D? D is a matrix. D is a matrix for the change basis from B to B to B1. From B to B1. Okay, this is the way of writing. D is a matrix change basis 2 to basis 1, or writing this way. Now, how to get D? This is the way. We just get technical details, right? You write the B2 here. B2 is there. 31101 minus 120. 300, okay, this is B2. We write the B1 here and perform row operations until this side is identity, or reduce the row echelon form. And this is D. So this matrix becomes D. D is what? D is change basis from B2 to B1. Okay. Then Find D inverse. Find D inverse. It will be the matrix change basis 1 to basis 2. Or there's another way that you write this one here, write this one there, exchanging the position, and you perform row operations, and this side will be D inverse. Okay. Then next one is E. What's E? E is a change basis from basis 2 or basis 3 to basis 4. So let me show you. Okay, basis E is a matrix changing the base 3 to basis 4. This is one way of writing, and this is another way of writing it. Now, how to get it? It's very easy. Write this side is base 3, and this side is base 4, and perform row operation until you get to reduce the row echelon here. And this is my E. This is my E. And find the inverse. You get change basis from basis 4 to basis 3. And then F. What's F? F is a change basis matrix change basis from B1 to BS3. Okay. This is the matrix. And why this, this is exactly base 3. No. 101. This is exactly B1. Yeah, this is exactly B1. Why F is exactly B1? Because standard basis is an identity. This side is identity, so we don't do any row operations. That side, which is B1, is the matrix of F. And so is G. G is from B3 change to BS3 2. B3 changes to BS2. Yes. So since this is identity already, so that matrix, that B3, this one is the matrix for change basis. And then you find the inverse, you find the other roots. So in other words, we can find all these matrices, the red ones. Okay. Of course, you can practice at home, yourself. Then you will familiar with derivation over these matrices. Okay, then let's pick up some verifications for let's have a verification for these matrices. First example, we pick up this element, this vector rather, this vector in a standard basis. BS3 is this. So 1, 3, minus 2 is a vector with respect to standard basis in R3. We want to transform. We want to go to here. We want to end up after transformation, end up here. So we want to start from here and end up there. Of course, you have many routes. Well, you have several choices. You can go B first, then G inverse. You get the root, right? Or you get F inverse first, then A. You reach that one. So let's do these two. Let's take a root from BS to BS3. Go with B, okay? B first, reach there. Then G inverse, you reach B3. Okay? Then it means that you pick up the vectors in this basis. Go B first. So multiply by B. This is a B. This is a B. Then multiply by G inverse. This is G inverse. And this will be the result. That is the vector in R2 in basis 3. That is root 1. Okay, take this root. And I can take another root. This root is from BS3. First goes with F inverse, then A, reach there, right? So this is the vector I pick up. Then times F inverse, then times A. This is F inverse. This is a vector. This is A, and you get the same result. You get the same result. Now, if you choose a more complicated routes, for example, I start from here, right? I want to finish there. I choose F inverse, then D inverse, then a C, then E inverse. I reach the same place. Okay, let's show again. I go here, and then this, then this, then this. Okay, this means F inverse, D inverse, C, and E inverse. So this is my vector. This is my F inverse. This is D inverse. This is C. This is E inverse, and you get the same result. Well, it's just amazing. Okay, now let's choose another example. We pick up 2 minus 1, 1 in the basis 2. So that means we pick up a vector here in a basis 2. We want go to R2 in basis 3. We want to be here. So we start from here, we want to end up there. So we have many routes to choose. You can choose this way, right? D and A, which is this one. We can choose C and E inverse. Okay, you can choose D and F and a B and a G inverse. See? Now, okay, this root is a C, then C inverse. So this is the vector times C, then times E inverse. This is vector, this is C, this is E inverse. We get this result. And you can choose a D choose D, then A. Choose D and A. So okay, this is the vector. This is times D first, then times A. So this vector times D times A. You get this result. Or you choose a crazy way. Choose a crazy way. D. You can go D first, then F, then B, then G inverse. Okay, D, F, B, G inverse. So you use this vector multiplied by D first, then times F, times B, times G inverse. And by listing these vectors and the multiplication, the matrices satisfy the associative law, right? You can multiply this way. Whichever way, you get the same result. Now, I think if you really interested, you can practice. You can pick up any. You can choose any vectors in any basis. You want to end up with, the other side, any basis you want, and you choose different roots. And amazingly, you get the same result. Of course, all these details, firstly, you have to understand the basic concepts. The transformation, Canyon basis, matrices, and vector space, all these basic concepts, the calculations are trivial, just straightforward. Okay, I hope that brings something which is interesting, and I hope you like it. Thank you for your watching.